that they don't like people standing. One of the 4 co-chairs of NeurIPS, and it's my great pleasure and honor to introduce you the speaker for the Breiman lecture, David Spiegelhalter. David is a statistician in the Center for Mathematical Sciences at Cambridge University and currently president of the Royal Statistical Society. His background is in Bayesian statistics, and he jointly developed the Lauritsen-Spiegelhalter algorithm for exact evidence propagation in Bayesian networks. He then led the team behind the Bugs software for MCMC analysis of Bayesian models, and he is chair of the Winton Center for Risk and Evidence Communication, which aims to improve the way that statistical evidence is used by health professionals, patients, lawyers, and judges, media, and policymakers. David has over 200 refereed publications, and he is co-author of 6 textbooks, as well as The Norm Chronicles with Michael Blastland and Sex by Numbers. He works extensively with the media and presented the BBC4 documentaries Tales You Win, The Science of Chance, and also the award-winning Climate Change by Numbers. He was elected Fellow of the Royal Society in 2005 and knighted in 2014 for services to medical statistics. Among his greatest achievements, we want to remember his participation in the 7th episode of Winter Wipeout in BBC One. And I would like also to mention that he is currently the world champion of loop and elliptical pool game. So please, David.
Okay. Thank you very much indeed. Okay. Well, thank you very much indeed for the introduction. It's a huge honor to be here and rather terrifying here. I've never spoken in a car park before, but this is always the first time. And I'm sorry, this is really embarrassing, but could you just smile, please? I've got to get... Great. That's one for the archive. Okay, so as you heard, I'm a statistician, and therefore it's very appropriate that I'm doing the Breiman lecture. Leo Breiman was an extraordinary man who sadly died in 2006, and he was one of the first statisticians to realize that there is this huge connection with machine learning and that these areas must come together. So if we look at his record on Google Scholar, we can see the classic classification and regression tree book from 1984. I remember buying it then. That was in a previous summer of AI. But also, of course, random forests and bagging have made him a hugely important and cited name in machine learning. And I suppose I'm trying to, in my small way, to carry on that tradition, to show how the connection between statistical ideas and machine learning can be so important. As was said, I've had a sort of history in this. Again, back in a summer of AI, I used to work on uncertainty propagation in Bayesian networks, and there was the early uncertainty in artificial intelligence conferences in the late 80s, a really golden time, and so that led to extra work. But also then, the idea of Bayesian graphical models was realized at the end of the 1980s as being incredibly important, and that led us to develop the Bugs software, which has led to STAN and all the other wonderful work in Bayesian MCMC. Okay, so, but as was told, since then, in the last 10 years, I've really gone over almost into the entertainment industry. I've gone into communication, so making documentaries for the BBC, appearing on reality shows like Winter Wipeout, and as was mentioned, I am world champion of Loop, which is a pool table with one hole and an elliptical shape. But but my main, the work I want to talk about some of today is by this team. This is a group that now I'm chair of in the maths department in Cambridge, but none of them are mathematicians or even statisticians. 4 psychologists, 2 ex-BBC communication people, web designers, all of whom are concerned with the communication of risk and evidence and science, and to evaluate those communications in an empirical and formal way. So that's my running theme. Okay, so what am I going to talk about? I'm going to dot around a bit with some historical, suitable for an old person like me, some historical stories. I want to talk about trust. I want to talk particularly about structure for evaluation. And then I want to talk about statistical methods for ranking a set of algorithms, layered explanations, explaining regression models, communicating uncertainty, and all of this, how some fairly basic statistical science might help in these issues, particularly on explanation. My primary focus is on medical applications because that's where I've worked on traditionally, but I hope the general ideas are important, and of course I can only scrape the surface. Okay, trust. Anyone in the UK who talks about trust immediately goes to this woman. She's Baroness Onora O'Neill. She's a philosopher of Kant, and she is an extraordinary person. I really recommend her TED Talk. 9 minutes on trust with jokes. She's brilliant, absolutely brilliant. And she has had a big influence with just a few, I'm going to mention a couple of times, a few little nuggets of wisdom she has boiled down. And one of the first ones says that organizations should not try to be trusted. That is the wrong objective to want to be trusted, because that is not in our control. That has to be offered up to us. We have to earn it. And the way we earn it is by demonstrating trustworthiness. So I'm not going to mention trust anymore. I'm just going to talk about demonstrating trustworthiness. This has become incredibly important. In the UK, the Office of National Statistics has got a new code of practice, and the number one aim is to be trustworthy. Not to be trusted, to be trustworthy. Okay, so what does that mean in this context? Well, we see lots of claims about algorithms. Here's just a few, that have come out recently in the UK about the skills in medical diagnosis. I'm not saying these are wrong claims. I'm just saying this is the sort of claim that's being made all the time. And I think this is one of the running themes throughout this talk, and I think it's quite important, is that we should be making trustworthy claims, we should expect to hear trustworthy claims from developers, both about that the system is trustworthy itself, so the trustworthiness of the claims made by the algorithm, but also the trustworthiness of the claims made about the algorithm, about how good it is, and about what its impact might be. So those two things, which are connected, but they're very useful to keep them separate. What the trustworthiness of the system itself compared with what is said about it. And I'm going to be looking at both of those today. Okay. One of the first contributions that I think statistics can make in this is by looking at its huge, long experience of evaluation other technologies or pharmaceutical drugs. There's a massive amount of experience in research design and in what I would call the phased evaluation. And it's completely standard within the medical industry, the pharmaceutical industry, that the development of a new drug follows a 4-phase pattern. Phase 1 is just safety testing in individuals, healthy individuals, volunteers. They get paid to have to take drugs. Yep, and it's not always safe. Phase 2 is what you might call proof of concept. It's testing on selected individuals to get an idea of the optimum administration, optimum dosage, and so on. Because all of this is building up to phase 3, which is the crucial thing. And these are the big randomized controlled trials. These are the ones that are submitted to the FDA for approval. If you've got 2 significant trials, big independent trials, then possibly your drug will be approved for marketing. And after that, you go on to phase 4, which is post-marketing surveillance for safety monitoring for adverse effect when it's out there in the community being used. And what I'd like to suggest, and it's not just me, there are many other people have suggested this over the last 40 years, in fact, or 35 years, is that within the area of algorithm development, there's a very neat 4-phase structure that we see about us all the time. And the first phase we might call the digital testing. That's the standard testing on test sets and the standard stuff that we all everyone does when they're just working on the computer. The next phase is the laboratory test. That's where you start opening up the system to users to see what they think about it. It's when you do develop the interface, where you're using user-centered design, and look at its accuracy when perhaps compared with real people. Phase 3, which actually very few things get to, is to see what is the impact when it's put into society. In other words, what is the marginal benefit? It may look good, it may be as good as an expert, but actually does it help anybody when it's put into practice? And then phase 4, once a system is in use, is its monitoring in routine use, it's essentially its safety pattern over time. And I'm going to just talk about some of those phases, the work that's been done, and some ideas that might be useful. Okay. First one, digital testing. This is maybe a bit of a sideline, but it's something I'm very interested in. I'm really interested in league tables, in ranking. I've done a lot on ranking hospitals and ranking schools. And so when I see a Kaggle competition, and I see algorithms being ranked, I want to say, well, is that a good ranking? How sure can you be about that ranking? How can you be that the one that's at the top is the best? And so I'd just like to talk about that. Okay, now a little distraction. I come from North Devon, beautiful place. Recommend it for holidays. Ilfracombe, very nice, beautiful resort on the west coast of Devon. In the churchyard at Ilfracombe, I found a gravestone, and that gravestone, wait for it, I bet you can guess what's going to happen, is to Francis William Somerton, who perished on the Titanic disaster in 1912. Yes, you were right. We're going to hit the Titanic. Sorry, it's unavoidable. And so he died. He went down, with the Titanic. He was traveling third class on his own. It's pretty likely. And so, actually, as a terrible bit of marketing, I decided to look at the Titanic data to plug it into a book I'm writing that's coming out next year. So it's just too good an opportunity to miss. So there is, you can download, you don't have to do the Kaggle competition because the Titanic data is just freely available online. Anyone can get the whole lot and cheat if they wanted to, not that I'm suggesting you should. But anyway, you can download it and look at, Francis Somerton, who paid £8 and a shilling for his ticket, travelling third class from Southampton. He really had a very low chance of survival. So, I'm going to copy the structure of the Kaggle competition. Who's had a go at the Kaggle competition? Yeah, good. Quite a few of you, yeah, okay. Well, you're among 59,000 people who have tried. So there's 1,300 passengers. I'm copying the thing of taking a training set of random 70% and a test set of 30%. And so which is the best algorithm to predict who survives? Okay, there's just Maria Scolaridou helped me for this, which I'm very grateful for. We did not, these are not optimized. This is using the algorithms from R-Caret applied. We're using default values, 10-fold cross-validation in the training set, nothing fancy at all, no complicated feature extraction at all. So really this is very crude. This is pure demonstration. And there's a list of some algorithms and their accuracy, but I'm more interested in, because I'm interested in probabilities, I'm interested in mean squared error, of the probabilities that come out of these algorithms. So what is the mean squared error, which I'm going to call the Breyer score. Statisticians call mean squared error for binary predictions. They call it the Breyer score because it's based on Breyer, who's a weather forecaster in the 1950s, and because it's a standard metric for evaluating weather forecasters and any other probabilistic prediction system. Okay, so actually the simple classification tree came out both best by a little bit on both of those categories. That's the tree. Many of you will have seen simple trees like that. Okay, so William Somerton, immediately, he was a man, turned left, so he was given a 16% chance of survival. Okay, so we can look at those Breyer scores for the 9 different algorithms, and there they are ranked with the simple cart at the top, and by a small margin it wins. And the immediate thing you might think of as a statistician is to put an error bar around that mean squared error, which is a straightforward thing to do, calculate its standard error on the test set, and we get those error bars. Now, that looks as if the top 7 algorithms are essentially indistinguishable. That is completely wrong. That is the wrong, misleading graphic to do. And it's because they're not being tested on independent sets of data. They're all being tested on the same data. We've got a paired analysis. And I've seen a recent paper by a very prominent team that compared a doctor and an algorithm tested on the same case by looking at their accuracy and how likely one was to be better than the other, assuming they were independent, which gives a grossly misleading assessment of their comparison. So that's potentially a very misleading graphic. We have to look at the differences on individual cases and to look at that measure, the difference, and do a standard error on that. And when we do that, we realize, yeah, the first 4 are not statistically significantly different from the winner. So CART was the best, but there's 3 others that were not statistically significantly different from that. And once we get down to the complex CART is just about, yeah, that's p less than 0.05 being different from the top one. So there's some at the top which are not significantly different from each other. Okay. So how confident can we be that CART is actually the best of those algorithms? What should Kaggle be doing instead of just ranking? Well, we can rank algorithms. What we can do is do a bootstrap sample from the test set, and then which is sampling with replacement, a set of 412 observations from the test set, and then rank the algorithms on that bootstrap sample, and then repeat that 1,000 times. And what we do is we get a distribution for the possible rank of each algorithm. So it's a really straightforward thing to do. This ranks the actual algorithm. If we wanted to rank the method, we'd have to bootstrap the training set data as well, which is more complicated. We have to repeat the whole process. And then we get these very nice pictures, which essentially are the probability distribution for the true underlying rank of each algorithm. And we can see that there's a big spread. Random forest could be almost anywhere. We don't know whether it's good or bad, essentially. And we can get a probability. We can now say that there is a 63% chance that simple algorithm, in fact, does go at the top in terms of mean squared error, but 23% chance the neural network is also top, and 8% chance the random forest is top, which gives us a very fair criteria when we're making comparisons. We stop just because something looks the best is not necessarily it is the best. We know that for football teams, we know that for schools, we know that for everything. We should be doing the same for algorithm. Okay, just a quick little aside, something which I think is a very nice thing to do is, who is the luckiest person on the Titanic? Any volunteers? I think it was this man, Carl Dahl. He was a 45-year-old. He is the man that when averaged, the survivor that when averaged over all the algorithms in the test set, got the highest Brier score. In other words, he was the most surprising survivor. He's the one who should have died but didn't. And we can actually find his story. He jumped into the water and then climbed onto lifeboat 15. They didn't want to take him. So I think he's the man you can see there, just trying to climb into the lifeboat. So I think he just fought his way on, actually, by brute force. He survived, anyway, and the others didn't. And poor old Hannah Somerton, William's wife, was left in Ilfracombe with just £5 to her name. Okay. Quickly now, on to phase 2, laboratory testing. Now, this is something that's becoming very popular, using what you might call, it's a kind of analogy of the Turing test. Alan Turing's making his first appearance this morning. So if we go back to 1950, Turing's classic paper introduces the idea of a Turing test in which an observer has to try to tell the difference between a computer and a human. And that's the Turing test. The method, is not... People aren't doing exactly that, but they're doing a quite similar thing, which is where you take a set of doctors, a random set of doctors that you might use as your to compare the computer with, and one of them is a computer. You don't know which one, and then you give them a whole lot of test cases, vignettes, and they exercise some judgment, and then those judgments are seen by other judges, other assessors, but they don't know which is the computer and which is the human. So they don't try to guess which is which, they just assess their scores. And that enables you to make a sort of comparison of the comparative accuracy or skill of the computer compared with the human in a blind way. And so that's what's being done. It can actually lead to some very odd results because what it can reveal is that there's no gold standard. In a classic test of this in 1970s by Ted Shortlift's team, they found that the algorithm, it was thought 30% of the time to be unacceptable, but the doctors were even worse. Colleagues just disagree. And so this guards against the idea there is a gold standard. These are being done at the moment. Just recently in June, Babylon AI with its diagnostic system, which is getting a lot of publicity, carried out such an evaluation, and there was a lot of publicity that it was as good as a doctor's. That's been quite strongly criticized in a very recent paper just a couple of weeks ago in The Lancet, in which they take apart this evaluation. Saying that one of the doctors was very bad and that these were selected cases and there was no statistical testing between them. But actually they did say that they were pretty impressed by Babylon and what it could do. But their crucial conclusion is that this is only the first phase. Well, actually, it's the second phase of the evaluation. And we can't know the benefit of one of these systems until we see how it works in practice, in routine practice. So what they were appealing for, and they provide a nice, again, phased structure for evaluation, is to get onto phase 3, field testing. Now, this is when it gets tricky. And I'd like to talk about some experience I've had in designing a actual randomized trial of a diagnostic aid in medicine. It's called a pragmatic study. In statistics, we make a distinction between an explanatory phase 3 study where you tightly control everything. You make sure everybody does everything exactly. And a pragmatic study where you essentially just put it in and see what happens. You really try to imitate routine practice. And this was we did what's called a cluster randomized trial because there are alternative study designs. We're all used to A/B testing, where you randomize individuals to receive different versions of websites, perhaps. So that's fine, but actually with these systems, algorithms have got an educational purpose. You're likely to get contamination. People are likely to do well in the cases where they're not using the system. So we did in the past a cluster randomized trial. That's where you randomize the doctors or the teams or the institutions to get the intervention. And that allows for learning effects and so on, and makes you realize that a system can benefit people in more ways than just what it tells them right in their faces. The third design, which some of you may know about, but is becoming incredibly popular in a lot of areas of healthcare interventions, is a stepped wedge design. A stepped wedge design is when you roll out a piece of technology to different sites in a tightly controlled way. Essentially, you randomize the order of who gets it first, second, third, fourth, fifth. And every month you put it into a new site, but you're monitoring all the sites at the same time, what their performance is. So you're getting contemporary balance between people who've got it and people who haven't got it. We're about to carry out one of these with one of our systems, rolling it out to every centre in the UK that's doing transplants, but they're going to get it in a random order. There's a random order of the rollout. So there's a lot of stuff. Now, for each of these designs, you have to change the analysis, you have to change the power calculations, and so on. A lot of interest in this. We did a cluster randomized trial for acute abdominal pain in which we randomized 40 doctors over 2.5 years to either get forms, either be control or forms, or have the computer or have computer and feedback. It was a naive Bayes algorithm, and actually it was rubbish. It really was poor, and the only excuse for this is that it was back in 1983. That was I think it was a Commodore. It might have been a really early IBM PC that we put the thing on. And put lots of patients through this, but the algorithm really wasn't very good. It wasn't very accurate. It was grossly overconfident. And people didn't use it very much. They only filled in the forms about 2/3 of the time, and he used the computer about half the time. So actually, as a system, it was a real failure. It was sitting there in the corner of the A&E department. Nobody liked it, but it worked. It nearly halved the number of admissions and operations of people who didn't have an organic disease, who had non-specific abdominal pain, for whom an operation was a complete waste of time. It nearly halved that rate, and this was in a rigorous design. So why did such a useless bit of junk actually have an impact? And by going back and looking very carefully at the trace of what happened to people, what you realize is that the reduction in operations was completely explained by not intervening on these people with non-specific abdominal pain. And this was because the junior doctors were making more correct, confident diagnoses in A&E, in the emergency room, that this patient did not have appendicitis or pancreatitis. And they did this because there was a cultural change. By using the forms, the computer and the feedback and so on, there was a cultural change of being more confident about making an initial diagnosis rather than just passing it on for someone else to decide. and admitting the patient. So, and what that shows is that when systems go into routine use, they can have all sorts of unintended side effects. They could have unintended benefits, but they could have unintended harms as well, which again shows the absolute necessity for controlled evaluation. Phase 4 I won't talk much about. There's a very nice paper by Ted Shortliff in a recent JAMA in which he talks about the need for, when your systems are out there being used, constant surveillance of how they're being used for safety, for update the knowledge base, to check about any problems, etc., etc. So that's them, and not make sure they are fail-safe, they're not causing harm. Okay, so let's finish the evaluation part, the phase 1 to phase 4. Let's look at transparency. Let's look at transparency. Onora O'Neill has got a lot to say about transparency. She doesn't like transparency. Yeah, basically saying, just disclosure is not enough. You have to, if you're going to be honest and be trustworthy, you have to, what she called intelligent openness. And she wrote this in a Royal Society report on open data. Now, this again is a lovely list. This is why you study Kant for 50 years, so you can write a little list like this. If you're going to be intelligent openness, if you're going to be intelligently transparent, you've got to make the information accessible. People have got to be able to get at it. It's got to be intelligible. They've got to be able to understand it. It's got to be usable. It's got to meet their needs. And it's got to be accessible, meaning somebody, if they want to, should be able to check it. Somebody, not everybody, but somebody should be able to check it. Now, that's a really useful little checklist to have that in your mind. Every time you're thinking about building an interface or providing information, have that little list in your mind. Because there are a lot of lists around. I like, in terms of the, explanation and accountability, I like the FAT-ML one. Why I like the FAT-ML one that they've come up with, these 5 features, is that it doesn't include transparency. They've realized that transparency is just a means to an end. It's not an end in itself. We have to think about, why do we want to be transparent? What are we doing with that? Well, I think the only thing I think that's missing from that is that I do think that, if you're talking about social impact, you really have to look at impact. What is the harms and benefits in practice? So there's one more line I think could go on there. Okay. The other thing, this is a classic thing, transparency does not necessarily imply interpretability. Remember back on the Titanic data, I built a complex cart. Yeah, okay, it's very transparent, completely uninterpretable, in terms of as an algorithm. Okay, so that's easy. So explainability and interpretability. Lots of people have made lists, lots of people have talked about this, so I can only just go through some more lists, but very quickly. There's usually a distinction between global and local explainability. Global explainability is about the quality of, or the trustworthiness of the algorithm itself, and where, in terms of its empirical basis, who it's been tested on, can you understand how it works, what in general are the important bits of information, and, what I would add is, what are the evaluations that have been done on it? This is the general, this is a general trustworthiness of the algorithm as a whole. The local explainability is to do with this particular case. Okay, why was this conclusion drawn? What was the tipping points? What if the inputs have been different in the counterfactual argument? Is this case actually within its competence? Is it an outlier? Can it detect that outlier? And how confident is the conclusion? So that's to do with the trustworthiness of the claim on this case. I think a very nice example from a team that in Britain that had been developed in Google DeepMind, working with Moorfields Hospital, a recent paper in Nature, talk about a system for essentially interpreting eye scans, 3D eye scans, in order to draw a triage, decision, and a diagnosis, in which they've really, rather than just going straight for a probability of a diagnosis, they've really tried to show the intermediate steps, these segmentation maps, where they can actually illustrate the chain of reasoning that have led them to, even though it's worked through, through deep learning, through to the final conclusion. So what I'd like to do now is just illustrate show you some work we've been doing on an NHS Predict system, and I'm going to see if I can make this work. Let's let's see if I can make this work. Okay, this is a system for women who've just been diagnosed with breast cancer and are going to have surgery and have to decide about extra treatment they might have, whether it's chemotherapy or hormone therapy and so on. And we spent a lot of time putting a front end on this, this algorithm. It's a statistical algorithm. Putting a front end and doing a lot of user testing, working with psychologists, etc. And the whole idea about this is that it's used by doctors in a group to make to decide what they think should be recommended to the patient, but increasingly it's being used in the discussion with the patient when we're talking about it. And I've known, friends of mine have used this device in order to argue back against the doctor, saying, I don't want that. The benefit is not big enough for me to put up with the side effects. And so it is actually, I think, we're hoping this will be empowering to women to make drawing their conclusions. So basically, you put in your data in the usual sort of way and decide what treatments you might like, or the possible treatments, and then it presents the results in many different ways, because the psychological research shows there is no correct way of explaining what the predictions are on this individual. There's no correct way to do it. One size does not fit all. You've got very different preferences depending on people's numerical or verbal or graphical skills. So we just provide a lot. You can choose what you want. The doctors like just like a table, because that's very simple for them to use in their own discussion of what would be the additional 10-year benefit. We could do 15 years, but 10-year benefit from 64% survival goes up to 81% if they have all the treatments. There's lots of helps. There are lots of help commands all over the place. Okay, but some people like survival curves. People who've done experiments, people can understand survival curves. With good annotation and a bit of help and support, they can understand survival curves. The interesting thing about this one, and this is one of the innovations, is to put in the dashed line. Oh, yeah, you're not seeing any of this. I'm bashing away, and you're not seeing any of it. Oh, what a waste of time. Didn't anyone tell me? Okay, sorry. Right, I'm going to have to, I can't do it. I realized that the thing is just working off PowerPoint. Okay, if you just excuse me 1 minute. Oh, what a waste of time. Sorry, someone should have let me know about that. I have some slides, I hope. Shit. Oh, I'm sorry. Beg your pardon, right, okay. Bugger. No, sorry, pardon my language. Okay, just a moment. Yes, that's what I wanted to be showing you. Yes, right. Thank you. Come on, you've got to tell me. I know I'm slogging my guts up here, and nothing there. So that's the table that people see, survival curves. You can see the nice thing about that, the dashed line shows what would be the survival for someone who's cured. In other words, that's the best you can do, best you can hope for. And so what you can see is that all those treatments take up a lot of the slack before that. Into bar charts, nicely annotated, text of what does it mean for 100 people, known to be a very good way to communicate risk. And finally, and this is one we thought patients wouldn't like, the icon array. What does it mean for 100 people like you in 10 years' time? What the patients didn't like is when these were little people, particularly when the deaths were black little people. So we've dehumanized it and decolored the deaths. This is the only place in the whole program where the word death is mentioned. Everything else is positively framed in terms of survival. So, okay, so that's one of the things that's in there. And we can put uncertainty on the benefits if you want to. You can get some explanation from tables. The explanation isn't great, but and we could do some more work on that. But you can do some explanation on that. Okay, so let's go back to where I was. Fortunately, I did have some already prepared. Always be cautious in that way. Where are we? Yeah. Okay. So yeah. So that's it. And this has got about 30,000 users a month. It's incredibly popular around the world. About half of those are in North America, half in Britain and Australia, whatever. And we're about to start a phase 3 trial of supplying side effect information. It's already in use, the thing, so it's quite difficult to do studies on it. And we're launching versions for prostate cancer, kidney, heart, and lung transplants. Explanation. there's lots of explanation. The main explanation is the counterfactuals, the fact how easy it is to change the inputs and see how the outputs change immediately. So that is just the ease of use and the attractiveness of use is very important. But then we've got text and tables. You could download the maths, a PDF. Nobody ever does that, I think. And we can get the code. It's all open source as well. And these are for very different audiences. If you want to see all the competing risk model, you can. That's just part of it. And nobody ever looks at that. Okay. Actually, one thing I should mention, referencing the talk before, is that this has got so attractive, I think we're suffering from over-trust. Is that people actually believe this is the truth, what's going to happen to them? And of course it's not. It's not. It's really quite crude. I'm sure you could build algorithms that would improve on it a little bit, particularly with access to more data. There's lots of features that are not in there. So it's very dangerous to make it almost, we've got to be really careful not to make people believe it too much. Okay, interpretability. Lots of just general comments. Variety of audiences, of course. There's no single way to do it. There's maybe some increasing legal demands, although that's not quite clear. You need to properly evaluate explanations. They may confuse or mislead. There's all sorts of really clever stuff you know about being done about surrogates or explaining black boxes. Oh, the other option, of course, is do you build an interpretable model in the first place and not bother with a complex model? And of course, regression models are apparently supposed to be interpretable because scoring is interpretable. So nice risk scoring work being done on generalized additive models, optimizing integers to produce indices such as that, just based on integer scoring, very simple, explainable output. What's interesting, of course, is how, what class of problems will this work in? What class of problems is it possible to construct an algorithm that's essentially not significantly different in terms of its accuracy and its performance, and yet has a much more interpretable format? I think that's an important issue. Just to point out, Alan Turing, of course, approached all this in explanation. He, when he was breaking the Enigma codes in the Second World War, used weights of evidence as his main way of communication, which are log likelihood ratios used in a naive Bayes model, and Jack Good promoted these in the 1950s. So these are essentially, additive forms of scores. The attractive thing about that, and you saw that in Cynthia Rudin's model before, is that you can have positive and negative scores. And positive and negative scores are very nice because you've got this sort of account. You can see what's evidence for a hypothesis and evidence against. And so, we did some work ages ago where in a system for diagnosing dyspepsia, stomach problems, where you could see the evidence for peptic ulcer and evidence against the peptic ulcer. And these just add up. This is a logistic regression, normalized, and you end up with a total probability of 68% chance they got a peptic ulcer, and that's well calibrated. It means 68%. But it's a very simple thing to explain because you can see a positive and negative account of what's going on. Now, just briefly, I've got two final little themes. Communicating uncertainty. Statisticians are obsessed about uncertainty, the second-order properties, and getting it right. And it's very nice to see in the FAT-ML guidelines to determine how to communicate the uncertainty margin of error of each decision. I'm going to go, again, slightly off track, but not apologizing, into general communicating uncertainty, because it is a part of trustworthiness to acknowledge that we don't know. But there's an anxiety that if we admit we don't know, will people believe us? Will they say, oh no, I'll go and talk to someone who does know, in politics or something like that. And we're faced with that, routinely, even from very good sources. Here's the BBC in January this year saying that unemployment in the UK had gone down by 3,000. Is that a trustworthy number? It's from the BBC. It's from the Office of National Statistics. Surely we can believe that number. Well, if we go down and dig hard, and you have to dig very hard, into the website, into a small set, into a big slab of text, we find out that the margin of error on that number is plus or minus 77,000. Well, actually, no, we can't believe that number. It might have gone up, it might have gone down. We haven't got a clue. So that is not a trustworthy communication. The uncertainty is not being acknowledged. Compared with the Bank of England, when it does its communication, it's full of uncertainty. These fan charts indicate 30 and 60, 90% chances of what might happen in the future and what GDP or growth might have been in the past. They don't know what's going to happen in the future, they don't know what's happening at the moment, and they haven't got much of a clue what happened in the past. And they're really honest about it. They're really upfront, and that's the Bank of England. We're now working on migration statistics. We thought we'd pick an area that wasn't very contested at all. So we're working with the Office of National Statistics on migration, and if you looked at the last report that came out a couple of weeks ago, that is the display, is what we call a fuzzy fan, not a straight line, there used to be just straight lines, to display the uncertainty on the migration statistics. It's going down very well. We're doing randomized trials to see whether people can understand it, whether they like it, or whatever. It's still inadequate because that's only the quantified uncertainty. There's all the other sources of error that are not taken into account yet. So I think communicating of uncertainty, our empirical research suggests that confident uncertainty, what I call muscular uncertainty, I'm uncertain, what are you going to do about it? No, we've got to be confident with our uncertainty, and that does not reduce trust and credibility. People expect it. People are not stupid. Now, what's the relevance to this audience? The point is that in the past, official statistics were based on big surveys. That is all changing. In the future, official statistics are going to be increasingly based on scraping routine data from all over the place, and there's going to be lots more uncertainty coming into that. And so I think this is an area where this community really needs to take some notice of. Okay, very finally. Oh yeah, great. Oh, finally, I got time. Fairness. Fairness. I wasn't going to talk about fairness, but I recently had a real example of a situation where a group of people really complained about an algorithm, said this is not fair. Okay. This was to do with an algorithm about heart age. If you Google, I hope you haven't got your laptop open, but if you have, Google heart age UK, and you'll come across this algorithm that was recently relaunched and was incredibly popular, got a huge amount of publicity. So there it is, and you put in usual stuff, you put in your ages and things like that. I'm actually 65, and it told me my heart was 69. Ah! So, and that's what... And nearly everybody, it tells them their heart is older than they are. And people just really annoyed people. Now, what is the idea behind this idea of what called effective age of your organs? There's lots of things. If you go online, you can find your lung age, your brain age, everything, your real age. Everybody tries to tell you that. It's actually a very rigorous way to communicate risk. I actually quite like it. It tells you what is the age of a healthy person, and somebody else defines what a healthy person is, who has the same risk function as you. So basically, if you've got your age and your risk, and then there's a trajectory of a healthy person and their risk profile, you map along and find out how old a healthy person would be who had the same risk as you, and in this case, is older than you are. This idea of heart age has been subject to phase 3 evaluation, not just phase 1, phase 2, phase 3 evaluation in a randomized trial in Spain in which 3,000 subjects were simple randomization to either get the heart age calculator, Framingham risk score, or control, and they found out that after a year, the people who had got the heart age had done more, had improved their behavior most. Their risk scores had gone down the most. So quite nice evaluation. Now, when this came out, I started receiving emails because I'm interested. People knew I was interested in this sort of stuff. So my esteemed colleagues, one said, what a load of from a maths professor. It just annoys me that it says I've raised risk factors when I've none, BBC producer. Actually, I think I've got to say this. What other bollocks this whole thing is. It might lose in the translation, but I think you get the gist, what that's about. That was from a doctor. I could have programmed this in my sleep, just a load of random numbers designed to people off. Okay, so this is what a random sample of my colleagues thought. They had something in common. They were all fit and healthy, middle-aged white men. Now, this is not a group we normally feel very sorry for, to be honest. This is not, I would not consider this a persecuted minority. So why were they so annoyed? And they were all given older hearts. They thought they'd put their things and it'll tell them how healthy they were, and then it told them their hearts were old. The point is, what was seen as not fair is that there's no question about how fit you are, how much exercise you take. And they know that is an important factor. These are all men who went out jogging and it still told them they were old and crummy. So they got so angry, really viscerally angry about this. It was seen as not fair. And actually, it wasn't very fair. What I didn't tell them is who was responsible for this algorithm. It was us. If they'd clicked down to the credits, they would have found that we'd written the thing and put it on GitHub. It's all open source, explanation, et cetera, et cetera. We were responsible for it. It was used by nearly 3 million people in the first few days, this algorithm. A staggering. We've got all that data now. Unbelievable amount of data. And the point is that we'd taken an algorithm that was already been developed on 2.3 million people. Again, a rather simple sort of competing risk Cox regression analysis, and then turned it into a heart age calculator rather than a survival analysis. We are now going to incorporate exercise into the algorithm just to give it a bit more face validity. So I don't keep on receiving abusive emails from my colleagues. I've had enough of that. Okay, so conclusion. So I'll just finish off. We need to demonstrate the trustworthiness of claims by an algorithm and about an algorithm. And we need to think about that all the time. And there is a phased evaluation of both quality and impact that addresses both of those characteristics. The evaluation actually talks about the trustworthiness of the algorithm, and the way in which the evaluations are communicated then asks us about the trustworthiness of the claims about the algorithm. I did a little statistical bit, but we can formally rank algorithms, bit of statistical stuff of that. Explanation, there's no correct way to do explanation. It depends on the audience. Multiple forms, multiple layers, but it's got to be evaluated. I believe in confident communication of uncertainty, and just to conclude, there are many reasons why people might feel an algorithm was unfair. And I suppose my plea is that really quite basic ideas in statistics might help in many areas. And with that, I'll give thanks to all the people who have helped me so kindly on this. Thank you very much indeed.
Thanks for a fascinating talk. I want to follow up on the NHS Predict system. So you talked a lot about uncertainty, how to explain that to users of the system, but I want to know a little bit about the statistical development behind it. So
sorry?
I want to know a little bit about the statistical development behind the Predict system. Specifically, what I'm interested in knowing is, since this is a what-if type calculator, where you could talk about counterfactuals, how did you assess whether you have support in the data for assessing any given counterfactual? Yeah,
the crucial thing is that the assessment of the risks based on the tumor size and things like that is purely observational data. It's a regression analysis, and we know those are associations. But the counterfactual about what if you did this treatment rather than that treatment, that is causal. That's not based on the observation. That is actually taken out of clinical trials, randomized clinical trials. And so those two sources of evidence are combined to construct the risk index. So we can feel confident that when they click on an alternative treatment, they are getting a causal effect on that one. The rest are just associations, and basically, and some of those perhaps are causal to do with tumor size or the number of positive nodes, and some are just associations, whether it's screen detected or detected symptomatically. It's just an association. You can't, that's not a causal route at all. Now, whether we could, we have not done enough evaluation on the explanation. I thought we'd have done more, because when I wrote the abstract for this, which is a shame, but that seems to be okay. As I said, we've got the text on describing the algorithm and things like that. Actually, 100 people looked at that over the last 3 months. I was amazed. We monitor this on analytics. So people have been looking at some of the explanation. But really, we expect those levels of explanation for really dedicated, different audience, a different audience. Yeah.
Great talk, thank you. I would like to follow up on the test set bootstrapping estimates for. So if the test set goes to infinity, the size of the test set goes to infinity, you underestimate your variability. But most of the variability then will come from training and maybe the training set size and the training procedure. So how do you deal with that? Most of the variability then comes from the training set or from the training procedure, like a neural network will not converge to the same minimum. So how do you capture that?
Oh, yes, as I said, that only works when you actually have got like in a Kaggle thing, where you have an absolutely fixed algorithm. And that's unchanged. You're evaluating a very specific actual algorithm, not the general method that's being used. No, it's much more complicated if you want to evaluate, if you're doing it internally to decide on what is an appropriate method to put into a complicated, because then really, I mean, I suppose a natural thing would just be to bootstrap the entire procedure again and again. Now, that could be very exhausting, so there could be some more efficient ways of bootstrapping in subsets or whatever, rather than trying to do the whole thing. But no, then you would have to bootstrap the entire business each time. Yeah.
Okay.
Thank you very much for your great talk. So my question is, I think how much trustworthy the algorithm is depends on which person is using that algorithm. So do you think it's important to adjust the algorithm to each individual, or do you think it's necessary to use the same algorithm for everybody to maintain trustworthiness?
I think the predict thing shows, I think you need the same algorithm for everybody, because it should be using the same level of skill on everybody. But people want very different levels of explanation. And so I think the crucial thing is to get layered. So for some people just don't want anything at all. Essentially they just want to be told what to do. Others would like to see more explanation, and they should be able to get at it. So you need pop-ups, you need just good design at the top level, but then you need layers where people can go down and find it so it can adapt to the user. And what we do, rather than at the beginning of the site asking people whether they were doctors or patients or experts or anything, no, it's got one site and people then explore it themselves. People are used to doing this now. So it's basically, do you want to know more? Do you want to know more? And using that format. Yeah.
Thank you very much.
Thank you for the talk. So I guess my question is about the relative versus absolute risk.
Oh, yeah.
So you said that heart age and brain age are very popular. But does that mean that that's the most important thing to assess? Because what if I have some 100 times higher chance of some very unlikely condition? Yeah.
Absolutely. Now, it's a bit naughty because normally I usually give talks on relative and absolute risk against relative risk and saying that you cannot make a rational decision without knowing absolute risks. And I still absolutely believe that. Heart age is a transformation of relative risk. It's because you could say someone who's 30 could use this and be told their heart age is 39. Well, their absolute risk is absolutely tiny of something happening in the next 10 years. But the relative risk. Now, so I'm slightly ambivalent about this because it basically has got a big emotional draw. It's got a big emotional impact. My body's old and this sort of thing. And it's deliberately being used for behavior change. And again, I'm not sure about this. We're not responsible for the way the algorithm's used. We just built it. It's like Werner von Braun. We just send them up, and somebody else's job where they come down. So, so I am slightly ambivalent about this because it does have such a big emotional impact. And people have criticized it because it could make 30-year-olds anxious when, in fact, their risk is incredibly low. The doctors, on the other hand, say, yes, but we want those 30-year-olds to change their behaviors now rather than waiting until their absolute risk when they're 50s and 60s gets high. So that's their idea, is that it is appropriate to use relative risk when you're trying to do long-term lifestyle changes. So it's a delicate business then,
Yeah, so there's a lot of concern about whether neural nets are safe and effective. And there's a recent bestseller, Weapons of Mass Destruction.
Yeah.
Right, where they ask lots of questions but don't offer many constructive suggestions. There's a lot of work on explainable AI, but I'm not very hopeful that it's really going to answer the question. And I kind of like the idea of reducing this to the drug test approach that you sort of described. But my question is, are the methods of deciding whether drugs are safe and effective, they don't get into mechanisms, that's what explainable AI tries to do, but are those mechanisms, are the methods that we use for deciding if a drug is safe and effective, are those methods safe and effective?
Well, people would argue about that quite a lot. They were brought in, of course, after thalidomide was the big thing that provoked the introduction of the controls. This is, it depends what you think about the way the FDA works. They, of course, have had to withdraw drugs after they've been on the market because of side effects being found long term. Now, whether that's appropriate is another matter, because often they are effective drugs. I mean, the point is that drugs can be both effective and unsafe.
Yes, but would you recommend that for neural nets?
Sorry?
Would you recommend the drug methods of FDA testing for neural nets?
I think elements of it, as I said, it's a very pragmatic idea. Does it work? You don't actually have to say, exactly why it works. I think it becomes more convincing, the argument, if you can say why it works. Explanations only based on association, you must think is going to be more fragile, because situations might change, and actually it means that you don't feel so confident about it. So I would believe a causal explanation was much more trustworthy than one based purely on past performance, and one based on the sort of thing that in that book, the Maths Destruction, Weapons of Maths Destruction book, based on like Compass as a proprietary algorithm for recidivism, I thought is the most untrustworthy thing you could ever think of, because it's both opaque, you can't get at it, it doesn't obey any of those criteria that I've been listing today. So actually, I do feel that the actual form of the algorithm, the mathematics behind it, I'm increasingly feeling is not the issue of great importance. For things like predict, if somebody had a good neural network, I wouldn't care less, actually. That would just be fine. I wouldn't mind too much, because what I want to do is use it, test it so extensively that I still felt confident about it. Yeah.
No.
One last question.
Yeah, I was wondering, so explainability of AI is one thing, but like there's the idea of too much information. So do you have thoughts about that?
Yeah, oh, absolutely. No, you mustn't bombard, because a lot of people just don't want to know. They don't want to know, they don't want to know. And so, no, you've got to really, people have got to want to see it, I think. And that's why, again, the layered communication. But it's got to be there if people do want to get at it. You can put a lot of work into something and nobody looks at it, but you've still done it. And that's part of being trustworthy, is to make sure that if people do want to see it, they look. And of course, though, once they start trusting the algorithm, then they don't bother with that. They just go straight to the answer. And then you've got the dangers of overtrust, I think. That can definitely happen. And that's a massive thing to monitor, to make sure that people don't become so reliant on it, they don't think about it at all. Yeah.
Thank you for the great talk.